Okay, so looking at rational functions again, here's this. Write the numerator as a product of three factors. So factor the numerator. They're saying it should break into three pieces. Technically, you do this using the rational zero theorem to select numbers that might be roots of the numerator, but I have a rather strong hunch that x minus 1 is one of the factors, so I'm just going to try that and see if it divides out. I'll do this by long division. Synthetic division works great too. So if we have x cubed plus 0x squared minus 7x plus 6, and we're dividing that by x minus 1, x goes into x cubed, x squared times x is x cubed, x squared times minus 1 is minus x squared. When we subtract x cubed minus x cubed is 0. 0 minus negative x squared is positive x squared. Bring down the next column, start again. X goes into x squared x times. That gives us x squared minus x. When we subtract, the x squareds cancel out. Minus 7x minus negative x is minus 6x. And x goes into minus 6x minus 6 times. So minus 6x plus 6. No remainder, so hooray, it worked. Our numerator factors to x minus 1, and the other piece is x squared plus x minus 6, and all that is over x minus 1. Now, we can do even better than that. X squared plus x minus 6 is a quadratic, and I believe that's factorable as well. As, let's see, it would be x plus 3x minus 2, I believe, if we want the middle to be positive 1x. That's x squared minus 2x plus 3x gives us plus 1x, and 3 times negative 2 gives us the negative 6. So yeah, that's our factored form. Okay, so there it is in factored form. Later, we're probably going to cancel out these x minus 1s, but right now we don't want to, because this x minus 1 is what reminds us there's a non-permissible value, or what we call a point discontinuity in this curve. If you just scratch these out and pretend that your curve is x plus 3x minus 2, you'll lose that discontinuity, and that can get you into trouble. So we won't do that just yet, but we've certainly got our eye on. We know these can cancel out. More about that soon. Okay, now determine the coordinates of the point of discontinuity. I'll just copy this down so we have it to look at again. X minus 1, x plus 3, x minus 2, all over x minus 1. So this curve is undefined at 1 because of this factor, but if you want to know where the missing point is, where the little blip is in the function, what you do is pretend for a moment that these have canceled out. We've noted that x is not allowed to be 1. But if those cancel, we're saying if we got rid of those two troublemakers and allowed them to cancel each other, how would the curve behave then? What if x were 1, and with these guys canceled out, there weren't any problem with putting 1 into the function? Well, then we'd get x plus 3 times x minus 2, which would be 4 times negative 1, so it would be negative 4. So if only we could plug in the point 1, we would get 1 comma negative 4. That's the location of our point of discontinuity. When we're drawing our graph, whatever it looks like, 1, negative 4 is where that little blip, or what we call the discontinuity point, is. State the zeros of the function. Those are the places where it equals 0. So if we have x minus 1, x plus 3, you might be way ahead of me on this one, but bear with me. I'm supposed to show all the work. We say that equals 0. So we can't really say there's a 0 when x equals 1 because the curve is undefined there. So that one's no good. But the other two give us zeros. We get x plus 3 equals 0, which would mean x equals negative 3. And we get x minus 2 equals 0, which would mean x equals 2. So those are the locations of the roots or x-intercepts or zeros of this curve. and use a graphing calculator to sketch f of x and sketch the graph on the grid. Without even getting the calculator out, we know that it's got to pass through 2, 0. It's got to pass through negative 3, 0. And it has a point of discontinuity at 1, negative 4. And scrolling up for a moment, we know that because the x minus 1 factors cancel almost everywhere, pretend those are gone for a moment, generally this curve wants to behave like x squared plus x minus 6. It wants to behave like a parabola opening up. And so, without the calculator even, I can tell you that this thing should have a parabolic shape. I haven't found the vertex. We could by completing the square if we wanted to. It behaves just like the parabola x squared plus x minus 6, with the exception of this one point where the discontinuity occurs. That's, in the end, the only effect that this x minus 1 term has. For every other number, this and this, the x minus 1s, cancel out. The one place where they can't cancel out is where they're both zeros, and there, for just a moment, the function doesn't exist. And as soon as we're past x equals 1, the function kicks in and continues behaving like a parabola.